Welcome to another tutorial in Ansys Workbench. In this tutorial, we are going to perform a topology optimization. Topology optimization takes a 3D structure and removes material to achieve the most efficient design. The object we are going to optimize is a circular disc 50 millimeters in diameter. The disc has 4 holes 5 millimeters in diameter. The outside of the disc has a torque applied to it, and the 4 holes are fixed, holding the disc from rotating. The goal is to remove any unneeded material in the disc. To perform a topology optimization in the disc, we first need to perform a typical static analysis. We then load in a topology optimization analysis system to perform the optimization. We want to have a relatively fine mesh to obtain a more accurate optimization. We will begin by building the model in SpaceClaim. We will then do a static analysis and then the topology optimization. After opening Ansys Workbench, I'll drag and drop a static structural. Then I will double click on Geometry to open SpaceClaim. Once SpaceClaim has opened, I will right click to select New Sketch Plane, select the XY plane, click Plan View to look at it straight on, click on the Circle tool, come to the center and click the center and drag a 50 millimeter diameter circle. Then I can remain on the Circle tool, go to the offset and click on the center of that circle, and these will be 5 millimeter diameter circles, and it's probably just as easy to create them individually around where they go. Now that I've created my circles, I can go ahead and pull this, so I will escape to leave the Circle tool. I can middle mouse button and rotate this around. I'll click on the 3D tool, I'll come and click on Pull, and then I'll highlight this interface and I will pull it back 3 millimeters. I can now come over to these surfaces and click on them and then right click and delete, and I'll delete those so I'm left with one solid. I'm now ready to go into to perform a topology optimization in Ansys Workbench. We first need to do a static solve. So after opening Mechanical, I can see that my geometry has been brought in correctly. My materials and coordinate systems have green checks. I'm ready to do a mesh, so I can click on Mesh, then click Generate, and I can look at the default mesh. I can middle mouse button and rotate it around to look at it straight on, and I can see that that mesh is pretty coarse, especially for a topology optimization. So to refine this mesh, I'll come up and click on Refinement, and I'll refine the mesh around these inner holes. So I'll middle mouse button and rotate the body back. Then I will click on the Surface Select tool. I'll click the first surface, Control click the remaining holes, and then click on No Selection and Apply. I can see that I have 4 faces, and I'll come down and click on my refinement and increase that to 2 and click Enter. I can see my mesh has turned pink, meaning that it's obsolete, so I can come back up here to Update and click Update. Now I can see that my mesh has been refined around my holes. To refine the mesh throughout the rest of the body, I will come to Mesh, and I'll come down to Resolution and change this 2 up to, I'll try 7. So 7, Enter. You can see again my mesh has gone obsolete. Here it's obsolete, and I can click on Update. I can see down here that it's processing and taking a while to generate this mesh. Looking at the mesh now, I can see that that is a nice looking mesh. It's very fine and will certainly work for a topology optimization for this tutorial. I'm now ready to apply boundary conditions and the loads. So to apply the boundary conditions, I'll click on Static Structural, Then I'm going to apply a cylindrical boundary condition to the inside of these 4 holes. So I'll click the drop down on supports and click cylindrical support. Then I will middle mouse button and rotate my structure. Click the surface select tool, which is the only one that can be selected for this type of selection. I'll click on the first cylinder hole, then control click the remaining 3 holes, come over and click apply, and you can see that these boundary conditions have been fixed in the radial, axial, and tangential directions. I'm now ready to apply the load, so I'll come up to loads and I'll apply a moment. So I'll click on moment and I'll pick this outside surface. So clicking on that outside surface, I can now come over and click apply. I'm going to apply this as components, so I'll click on the vector box and change that drop down to components. And now I want to make sure that the moment is going around the z-axis, so I'll come over here to the z-axis and enter in the moment. I can see that my units are in terms of inch pounds, so I want to come back up here to home, come to units, change my units to metric, and click on my moment again here and change this to 100 Newton meters. Click and enter. I now have my cylindrical boundary conditions and my moment applied. I'm ready to determine my outputs, so I'll click on solution. Then I can come up to solution and I will click on stress, click equivalent stress, and I can also click on deformation and click on total deformation. I'm now ready to perform a solve and look at the static solution. After the model has been solved, I can see that my total deformation seems like it makes sense. The largest deformation is on the outside of the disk, and down here in the inside of the disk I have 0 deformation. If I look at the equivalent stress, I can see that the stresses are largest right around the holes, which also. We are now ready to begin the topology optimization. To do this, we minimize the mechanical window, come over to Analysis Systems, and scroll down to Topology Optimization. We left-click on Topology Optimization and bring it over and drop it onto the solution under Static Structural. We have now created the Topology Optimization drop-down window. We can see that the engineering data, the geometry, and the model, as well as the solution, have been transferred. However, we need to make it so that the topology optimization is seen in the structure tree in Mechanical. So I need to come over to Results and right-click on Results and then click Update. Now when I come back to Mechanical, I can see that I have a topology optimization drop-down in the project tree. I now need to address each one of these items underneath the topology optimization drop-down. So I'll first click on Analysis Settings. This tells me where I can set the maximum number of iterations, convergence accuracy, a penalty factor. The main item that we need to be concerned with here is the number of iterations, and we'll go ahead and leave this as the default 500. We then click on the optimization region. This is where we tell Ansys what regions we want to optimize as well as those we don't. So under geometry, right now it's set at all bodies. I only have one body in this structure, so I'll go ahead and leave that as all bodies. On the exclusion region, it's defined by boundary condition, and then it's set for all boundary conditions. I can click on this drop down and I could set the exclusion region to be loads, supports, or none. Again, I'm going to go ahead and leave it on the default as all boundary conditions. My objective statement, I don't need to change anything. All I need to do is make sure that this check is enabled and the defaults are fine for this analysis. I then come to the response constraint, and this is where I tell Ansys what I want to optimize. And right now it's set at mass. If I click on this, I can see that I could optimize on volume, stress, displacement, and these other items. I'm going to go ahead and optimize for mass, so I'll leave it on mass. And right now it's set to retain. I'm going to go ahead and scroll that down to 30%. So we'll have a significant reduction in the mass. Also, you can set under optimization different objectives, response constraints where we could, for example, constrain the displacement at a certain point or the stress at a certain point to be a specific value. We have manufacturing constraints where we can require the optimization to be symmetric or such that the part could be extruded, and we can also constrain member size. Additive manufacturing constraints can also be set. In this tutorial, we will not set any of these constraints. I'm now ready to come to my solution and start my solution, so I'll click on Solution and click Solve. To view the solution and watch it progress, I can come to Solution Information and click on Topology Density Tracker. And now as my system is optimized, I'll be able to view the updates on my screen here. You can see that the system is running down here and that it's 1% complete. The optimization takes a lot longer than a single static solve because it's essentially changing the geometry and then doing another solve. If I click on Topology Density Tracker, you can see that the first update now has a lot of mass removed. Further updates will continue to now come back and add mass in so that the model is actually a valid model. While it goes through these updates, I'm going to go ahead and pause the. Once the optimization is complete, I can click on Topology Density to view the optimized geometry. I can watch the optimization process by coming down and making sure I'm clicked on Graph and then click on Play, and this will progress through the optimization process and show how initially a lot of material was removed, and then as the number of iterations progressed, material was added back into the structure. In order to validate this optimized design, we need to minimize the mechanical window, come over to Results and right-click, and then click on Transfer to Design Validation System. This will generate a new static structural window over here that will allow us to look at the optimized geometry. So we can see that the new static structural window does not have a geometry window in it. We need to make sure that the new geometry is transferred. In older versions of Workbench, the geometry module or window was brought in automatically. Here we need to click on this black arrow and then click on Recreate Deleted Components and then click OK. This will generate a geometry for us. Now we come over to Results and we connect the results by clicking on the Results window and dragging it up to the Geometry window and letting it go. Now our results from our topology optimization are connected to our new static structural window. However, we need to update each of these. This update process will take a few minutes between each one, so I will hit the pause during the updates. So to begin, I will right-click on Results and then click Update. After that is finished, I get a green arrow on Results, and now I'm ready to come up and I right-click on Geometry and click Update. After getting the green arrow or check on Geometry in my new static structural window, I can double-click on the geometry to open Space Claim and look at my new geometry in Space. So after opening Space Claim, we can see that the optimized geometry shown here in purple has been brought in, and we can also see shown here in green the original geometry. We have both components over here. If we don't want to see the original geometry, we can unclick that box, and now we just see our optimized structure. If we open the optimized structure, we can see that it's made up of facets. If we right-click on facets, we can convert all of these facets to a solid, but doing that gives us a very complex geometry. And you'll see that when we click on Convert Solid, Merge Faces, we get a warning saying, are you sure you want to make this complex of a geometry? So I'll go ahead and click No here. What we'll do now is show a few functions in SpaceClaim that allow us to come up with a much better geometry that can be more easily meshed. So I'll come here and minimize the drop-down tree, and I will come up to the Sketch tool and click on the Sketch tool. Now I can see that I need to select the plane that I'm interested in, so I'll click this front face and select the plane. Now I'm going to select all of these lines by using a box select. So I'll box select all of those lines, then I'll come over and click the Copy tool, and then I'll click the Paste tool or the Paste tool. And I can see that I have a copy of all of those original lines. I can also see that these curves have been generated. I can now stop viewing the original structure and the optimized structure and just look at these lines. So I'll go ahead and look at them straight on by clicking on the Z-axis. Now that I have clean lines around all of my holes, I'm ready to start on these other lines. To do these, what I'm going to do is simply create a straight line from this tangent point up to this corner. And then I'll come over to this tangent point and create another straight line. And I'll connect those two lines together. Then I'll come to my round corner tool and I'll click on the round corner tool. I'll click that line and then the second line, and I'll give that a radius of 2 millimeters. Now I can go back to my trim tool and trim all of these extra lines. This appears to be a very sharp edge right here, as does this one down here. So I'll come in and use the round corner tool again on these lines and enter in a radius of 1 millimeter. And I can do the same thing over here with the corner tool, and I don't want to delete that line, so I'll click here and then click here and enter in a radius of 1 millimeter and get a little finer curvature there. I can now come back to the trim tool and trim all of these other lines off of here. So I will go ahead and do that through the rest of the structure and then bring it back. Now I have my inner core looking much better. If this was to be a real design, I would likely want this to be exactly symmetric, and so I would need to be more careful about how I did the cutting and pasting. The last thing I need to do is come up here and generate some hole for these sections here. Probably the easiest way to do that, to approximate that, is to come up to the select the sketch plane and click on the ellipse tool, and then you click the center of the ellipse, you drag the major ellipse to the distance that you want, and then you drag the minor ellipse, and I then click, and you now have an ellipse. So I'll go ahead and copy that ellipse around to these 4 places and then delete the rest of these lines. I now have a much better looking geometry overall. I'm ready to pull this geometry, so I can click my middle mouse button and control and move it to the center, then click the middle mouse button to rotate it, come up to the pull tool, click on pull and select this face, and I'll pull this face the 3 millimeter width. So click 3, enter. So this will be the new structure that I go ahead and bring into mechanical. So I can come over here to all these other surfaces and I can either right click on them and delete them, or I can suppress for physics. I'll go ahead and delete these. I'll leave my solid and I'll click and delete these other bodies as well, so that mechanical doesn't get confused when I try to bring in all of that other information. So I now just have one solid. I can look at it straight on, and this will be the solid that I bring into mechanical. After opening mechanical, we can see that our clean structure has been brought in correctly. We can go ahead and mesh it, so click on mesh, click generate, and this will be the default mesh. Again, it's pretty coarse, so I'll come down here to resolution and I'll increase the resolution to 5. Enter. My mesh becomes obsolete. I click update to update the mesh. This mesh looks sufficiently refined for this tutorial, so I'll go ahead and leave that mesh. I'll come to static structural, come up to supports and click on cylindrical support. Click on the surface tool, and again I'll click these inside holes. So click the first one, control click the other 3, and then click apply. I now have those 4 faces, and I'm ready to apply my load. So I'll click on moment, I'll click this outer face, click apply, and come down and change from vector to components, and then enter a Z component of 100 Newton meters. I now have that, so I can click on solution and click on stress, equivalent von Mises stress, and then click on deformation and total. Now I can go ahead and solve this model. The results have come back, and I can click on equivalent stress, and I can see that my equivalent stress here is 2.9 e to the 8 pascals, and that's in these hot spots here on the inside of the bolt holes. If I go back to Workbench, I can go to engineering data and see that the yield strength for my material, tensile yield strength, was 2.5 e to the 8. So my new model has exceeded the yield strength. Likely localized deformation would occur here. I could also refine the mesh in this specific area to make sure that's exactly what's going on. But I would either need to account for localized deformation and strain hardening here, or I would need to go back and pick a different material, or go back and maybe make this a little bit thicker in the lengthwise direction, but to address that issue. So this goes to show that your refined structure may not meet the requirements that you need. Hopefully this tutorial has been helpful for you.